It's time to do the Elmo slide. Everybody flap your arms. Here we go now. Flap, 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 flap your arms. Flap, 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 flap your arms. Flap, flap.
In the first part of our lecture, our goal is to use what we know about semidirect products to classify groups of given order. And the first example we're going to do is classifying groups of order 30. So in order to do that, we're going to prove something that was an example on page 143 to 144 of Dumbit and Foote that we skipped over initially. And I'll explain why we skipped it initially and why we're coming back to it now. We're going to prove that every group of order 30 has a normal subgroup of order 15. And this is going to be the starting point for showing that we can understand groups of order 30 as semidirect products. So, all right, let's get started. Let's say that G is a group of order 30. Let P be a Sylow 5 subgroup and Q be a Sylow 3 subgroup. So what is 30? It's 2 times 3 times 5. So P has order 5 and Q has order 3. If either one of P or Q is normal in G, then this product set PQ is a subgroup of G. So by Lagrange, we have a subgroup of order 3, a subgroup of order 5. The intersection is a subgroup of G that and the order divides both 3 and 5. So it has to be 1. So the intersection is trivial. So that means that the size of this product set, P times Q, is 15. So if either of P or Q is normal, then here's our subgroup of order 15. And why is it normal? Well, a subgroup of order 15 inside a group of order 30 has index 2. And we know that every subgroup of index 2 in a group is automatically normal. Okay, so what do we need to prove this statement? Is we just need to show that inside a group of order 30, either a Sylow 5 subgroup or a Sylow 3 subgroup is normal. Okay, so I want to take a little detour and say that something better is actually true. What we'll actually prove is that if either of P and Q is normal in G, then both are normal in G. So what we'll see is that, in fact, a group of order 30 has both a normal Sylow 3 subgroup and a normal Sylow 5 subgroup. So why did we skip over this at first? Because the way that we're going to prove that this is true uses two exercises from the homework that we hadn't done at the time when it would have been natural to bring up this example, but we've done them now. So hopefully the ideas that go into this are now familiar to you. So we're going to use two exercises from section 4.4. This is the section of the textbook about automorphisms. We saw that if H is the unique subgroup of its order, of order equal to the order of H, inside a group G, then H is characteristic in G. Remember, what does characteristic mean? It means that every automorphism of G sends this subgroup H to itself. And the proof of this statement is like a sentence, because an automorphism of G takes a subgroup of given order to another subgroup of that order. So if there's no choice about which subgroup of that order to send it to, then it has to be sent to itself. Okay, the next exercise we're going to use is a piece of exercise 8 of section 4.4, just part A, which says, okay, let's say G is a group and H and K are subgroups of G, and H is a subgroup of K. If H is characteristic in K and K is normal in G, then H is normal in G. So remember, this was something that came up on the first midterm. If you have inside of G, if K is a normal subgroup and then H is a normal subgroup of K, that does not mean that H is a normal subgroup of G. But if you ask for more than H being normal in K, if you ask that H is characteristic in K, then H has to be normal in the group G. So I'll pause and erase. And first, I'll show you how to use these two exercises applied to this example to see that if one of PQ is normal in G, then both are normal in G. And then the rest of the proof here will just be to show that either P is normal in G or Q is normal in G. So now that we have the statements of these two exercises, let's suppose that P is a normal subgroup of G. That means that PQ is a subgroup of G of order 15. And we know that every group of order 15 is cyclic. Why is that? 15 is 3 times 5. It's a product of primes P and Q, where Q is not 1 mod P. So what does that mean? We have this cyclic group of order 15. A cyclic group has a unique subgroup of order D for each divisor D of the order. So Q is a subgroup of PQ of order 3. So it's the unique subgroup of PQ of order 3. And by the statement of this first exercise, Q is characteristic in PQ. So now, where are we? We have these subgroups Q and PQ of G. PQ is normal in G because it has index 2, and Q is characteristic in PQ. So by the statement of the second exercise, Q is normal in G. So that proves what we wanted to prove, that if P is normal in G, then Q is also normal in G. And if we do the exact same idea with Q and P reversed everywhere, we'll see that if Q is normal in G, then P is normal in G also. Okay, so I'm going to pause and erase, and then we'll show using Sylow's theorem that either P is normal in G or Q is normal in G by counting. Let's finish up our discussion of this example. We want to show that either P is normal in G or Q is normal in G. So what does that mean? We want to show that either there's a unique Sylow 5 subgroup or there's a unique Sylow 3 subgroup. So we'll prove this by contradiction. Let's suppose that N5 is not 1 and N3 is not 1. By Sylow 3, what does that tell us? N5 is congruent to 1 mod 5, and N5 divides 6. N3 is congruent to 1 mod 3, and N3 divides 10. So if N5 is not 1, it has to be 6. There are no other choices. And if N3 is not 1, it has to be 10. There are no other choices. But if N3 is 10, then G has 10 times 3 minus 1, that's 20 elements of order 3. And if N5 is equal to 6, then G has 6 times 5 minus 1, 24 elements of order 5. And this is too many elements together, right? If you have 20 elements of order 3 and 24 elements of order 5, then you have at least 44 elements, right? We haven't even counted the elements of other orders. But that's already 20 plus 24 is 44, which is bigger than 30, which is the size of the group G. So this is just not possible. So it must be the case that either N5 is 1 or N3 is 1. And because of the argument we saw earlier in the video, in fact, if one of them is 1, the other is 1 as well. So we have shown that every group of order 30 has both a normal Sylow 3 subgroup and a normal Sylow 5 subgroup. So not only is there a subgroup of order 15, but this stronger statement is true.